Good morning, student. Those who are present, please give your attendance in the chat box. Write your roll number write your enrollment number in the chat box. Good morning. Okay. So, like what we were discussing about the consolidation of soil, right? Till now we have discussed about the consolidation, right? What is consolidation? How consolidation is happen, and what are the effects of consolidation? Those things I have discussed, and how this consolidation is like you know how this consolidation is represented, and it is explained with the help of the spring analogy theory. I think those things also I have discussed. So, any question till now? Have you understand this spring analogy theory, student? Have you understand this spring analogy theory? How this consolidation theory can be explained with the help of a spring? At least you should give some response. No, then only I can understand. Otherwise, it's like I am just from one side I am just speaking only. Have you understand this theory? How this spring analogy is used to explain the consolidation theory? Student, do you remember or not? Do you remember or not that we were discussing about consolidation in theoretical engineering? Once again, okay, all of you or only one person is have doubt? Once again. So have you understand this consolidation? What is consolidation? What happens? But what is the difference between compressibility and consolidation? Have you understand the difference between compressibility and consolidation? Or shall I start from the start, present, from the first beginning? From here, from the beginning? Okay, compressibility is what? This is the like settlement of soil when if we apply a mechanical load on a soil sample, right? So there will be settlement, right? There will be deformation, and that deformation will happen due to the expulsion of poured air. When the deformation happens due to the expulsion of poured air from the void of the soil sample, then we call it the compressibility, right? Soil is compressed. But in consolidation, what happens when a fully saturated soil is loaded externally, water will squeeze out from the void spaces, right? And because of that, now there will be deformation. There is settlement of the soil sample. Okay, that is called consolidation, and this is one of the great example of consolidation. This is the leaning tower of Pisa. This is why it is leaning because of the there underneath this tower. No, there was a great, there's a very thick clay layer. Okay, once the construction begin, the the clay layer started consolidated. That means the water which is present in the soil sample, in the clay sample, start to squeeze out from the soil pore, and because of that there is a tilting of this tower. So this is a very great example. This is a great example of consolidation. Okay, so what happened? What is the main concept? So you can see this two-phase diagram. This is a two-phase diagram. There is only solid, soil and water. That means soil is fully saturated. So we can call it two-phase diagram, two-phase system. This is the soil and this is the water. See what soil cannot be, soil is incompressible. Only rearrangement can happen. If the soil is in loose state, if we apply some load, there will be a rearrangement of the soil particle. But soil particle will not compress. Similarly, water will not compress because water is incompressible. Right? So this is the initial state when we apply a load. Okay, when we apply at this stage, what will happen? Some amount of water will squeeze out because of the load. Because of the load, some amount of water will squeeze out. Can you see? This is the water which is squeezed out from the soil sample. And because of the there will be volume reduction. This is called consolidation. This entire process is called consolidation. Here, this settlement, whatever the settlement happened, that settlement will be equal to the volume of the squeeze out water. Whatever the water squeeze out, that volume will be equal to the settlement of the soil sample. Okay. So fundamentals of consolidation. So you can see this is a sand layer, then there is a clay layer, this is another sand layer. So generally in field, no, we may have different soil layers. So it could be possible that there will be only clay layer in some areas there will be only sand layer. But no, many a time what happened there will be different soil layers. Suppose there will be initially there will be a sand layer, then there will be clay again sand, again clay. This is how the layers are formed in the field. Okay, normally. So here we have taken one. We have taken that there is a sand layer, then there is a clay layer, and again there is a sand layer. Okay, actually this is what happened when we do a one-dimensional consolidation test. This is what happened. Actually, this sand layer, these are represented by porous stone. These are replaced by porous stone, and this is the clay layer. Okay, so since this sand layer, they are highly permeable. Okay, so what will happen? Water will flow out. Water will squeeze out from the sand, from the clay layer through the sand layer, right? Suppose we have applied the vertical stress delta sigma. We have applied the vertical stress delta sigma on the surface of this sand layer. Okay. So what will happen because of this application of vertical stress? What will happen? This soil sample are fully saturated. So initially, this vertical stress which will be taken by the pore water, whatever the pore water that is present in the soil sample, that will carry this delta sigma. That means there will be increase in pore water pressure, which is denoted by U or delta U. U is the pore water pressure. Okay. So, because of this increase in the pore water pressure, what will happen? Since there is a clay layer, there is a sand layer, and its permeability is very high comparing to clay layer. So, what will happen? Water will squeeze out from this clay layer, through this sand. Okay, so there will be volume reduction. Initially, what will happen? So when the water will squeeze out from the clay layer, what will happen? This vertical space will be taken by these clay particles. Since the water is squeezing out from the clay layer, so what will happen? That stress will be transferred to clay particles. Okay. So this is written delta sigma. This is the vertical stress increment causes U to increase immediately. That means at the immediate when we just T equal to 0 when we applied the vertical stress, that means at the time T equal to 0, just we have applied. What will happen? You will increase immediately. Immediately there will be increase in water. That is called excess water pressure. That is nothing but the excess water pressure. So with time, this excess water pressure will dissipate, and this delta sigma, this will transfer to the soil particles, that is present in soil sample. This soil particle will carry this delta sigma load. So what will happen in sand? Pore pressure increase dissipates rapidly due to high permeability. So since sand is a high permeable, it is highly permeable. So whatever the increase in water pressure, that will dissipate rapidly, very fast. But in case of clay layer, no, it will take time. With time, this water pressure will uh, and there will be compression. So because of that, these clay particles, the clay layer actually they take lot of time. Sometimes years, 100, 10, 20, 100 years. Okay. So this thing, see, can you see this figure? Can you see the figure? So at time of initial loading T equal to 0, what will happen at time T equal to 0 when we apply delta sigma vertical stress on the surface of this soil layer? What will happen? The pore water pressure delta U is the pore water pressure. It will increase immediately. See delta sigma initially in the first figure, total stress increment, okay, with depth. So there will be increasing water pressure, okay, and effective stress will be 0. Effective stress means is total stress minus water pressure. So if water pressure is maximum, that means whatever the stress increment that is equal to the water pressure, then means this effective stress will be 0. Okay, now what will happen between time t equal to 0 to t equal to infinity? In between this time, what will happen? This water will dissipate. This water will start to dissipate slowly in case of clay and in case of sand. So this can you see water pressure is increasing, right? It is start to decrease. Okay. So when the water pressure will decrease, no, then this effective stress will increase. Okay. And at time t equal to infinity, this water pressure will be 0 and effective stress will be maximum. Okay, soil skeleton has taken loading. Effective stress increase now equals to vertical stress increment. At time t equal to 0, whatever the vertical stress is applied on the soil sample, that will be completely taken by this soil skeleton. It is nothing but the effective stress. So this is the spring analogy method. Like uh, this actually what happened, like in this case what we assumed that this springs, no, these are actually nothing but the soil sample. So how these springs are behave based on that, this analogy, this theory is proposed. That means we have replaced the soil sample by a spring. Can you see the spring? So here, can you see the second figure? Can you see? We have applied different load, 20 Newton, 5 Newton, 10 Newton, 15 Newton, 20 Newton. This is how springs are, this is a compression. This is how the compression takes place in a spring. Now, if we think that, if we assume that there is a there is a spring which is completely filled with water. Okay, this is the spring, and this side this is a water. Okay, and this is a vessel. This is a vessel, and there is a outlet from where the water can squeeze out. Right now we have applied the W load. Okay, we have applied the load at the surface of this piston. This piston is movable. It can move. Okay, we can, like, it is movable. So what happened? What will happen? So when we apply this load to initially W, initially this entire load will be taken by the water present in here. Okay, since there is an outlet, if we open the outlet, you know what will happen? Because of this application of load, this some amount of water will squeeze out from this vessel. Now, just you think about, you have a glass of water and you will apply glass of water and you will apply the load on the surface of the water. What will happen? Water will squeeze out from the from the glass. Same thing will also happen here also here. But when we apply the load at the piston, no, some amount of water will squeeze out. And when some amount of water is squeezed out, the entire load will be taken by the spring initially. So there will be deformation initially. Again, there is a W amount of load. So again there will be water will squeeze out from this vessel. Again, once the water will squeeze out from the vessel, this load will be taken by the spring. Again, there will be deformation. And the same thing happens in soil also. Okay, so this is how the spring analogy theory is used to explain the consolidation theory. Is it clear, student? Is it clear? Okay, so this same thing. Okay, same thing. Similar phenomena. A load is first taken by water only. Water pressure slowly dissipates. Soil particles start taking load gradually. After some time, excess water pressure is completely dissipated through voids, and the load is carried only by the soil particles. This is what happened in case of consolidation. Okay. Now, how this I'll explain later on what is normally consolidated soil. So this is the one-dimensional consolidation test. This is given by Tarzagi. This is actually also called odometer test. This is the odometer. Okay, this is the odometer and this is the loading frame. So this is the odometer. Okay, okay. These are the odometer. Okay. These are odometer. These are odometer. There are three odometers are there. Okay, and these are the loading frame. And here we can apply the load. We can apply the load. There is a piston through which the load is actually given to the soil sample. If we give the load here, so this is the frame. So through this, okay, through this load will be, yeah, this will be taken by the soil sample. Okay, actually this is the odometer, and this is what happened. Okay, this is the line diagram of the odometer. Actually, this height is 2 meter. This height is 2 meter, and these are the wall. These are the wall. These are the wall, and this is porous stone. There are two porous stone. One is above, one is below the soil sample. This is the soil sample, and this diameter is actually 6 centimeter. 6 centimeter. Okay, and this is actually round. This is round shaped. Okay, this is 6 centimeter, and this is a 2 centimeter. This is the maximum height of the sample. So you can take it 2 centimeter. You can take 1.5. You can take 1 centimeter also. Okay, generally we take 1.5 centimeter thickness of the soil sample when we do the experiment. And this is the another, this is where we put the water actually. This is a level of water. This is a level of water. Actually, the entire soil sample is under the water, is immersed in the water. That means the soil is fully saturated. What happened when we start this experiment? No, we prepare the soil sample. Okay, we prepare the soil sample and we keep the soil sample for at least 1 to 2 weeks. So, if sometimes 15 days is required to make the soil fully saturated. Saturation takes place 1 week to 2 weeks, 7 to 15 days. Okay, based on the plasticity of the soil sample. If it is highly plastic soil, then it takes around 15 days to complete the saturation. Saturation means the entire all the pore are filled with water. Okay. Once the soil is saturated, what we do? We start by applying load. Initially, we will apply 5 kPa load, then 10 kPa, then 20, then 50, 1, 2, 4, 8. Up to 800 kPa load we applied. And for each and every load increment, what we do? what we take the readings, like how much deformation is happening with time. Suppose we have applied the 100 kPa load on the soil sample. Here we have applied a load soil sample. So what will happen? There will be soil will start to, there will be deformation. Okay, so with time, that means 1 second, 2 second, 4 second, 10 second, 20 second, like this, up to one day, up to 24 hours. No, how this deformation is taking place with time. Those data we noted and we can plot it. We plot it in a graph and we find out what is the 90% concentration under that load. Again, we will apply another load, like we will increase the load. We will increase the load. This is so this is how we do the consolidation experiment. Okay, so in this is proposed by Tarzaki in 1936. Is proposed this one-dimensional consolidation theory, and what there are some assumptions made in this consolidation theory. The first one is soil is homogeneous. That means the soil particles are same. Okay, soil properties are same. Soil is fully saturated. Coefficient of consolidation remains constant throughout the soil mass and also remains constant with time. Coefficient of permeability is constant throughout. Darcy's law for flow of water through soil mass is valid. Okay, that means P equal to Ki. Consolidation is a one-dimensional problem. That is, water flows in only one direction and the resulting settlement also occur in one direction only. And soil particles are assumed to be incompressible. That is, all the settlement is due to the expansion of water. These are the assumptions made in the Karjaki's one-dimensional theory. The first one is soil is homogeneous. The soil properties are same. Soil is fully saturated. All the words are filled with water. So coefficient of consolidation, this I will explain what is coefficient of consolidation. This remains constant throughout the soil mass. Okay. This is another assumption. The fourth assumption is coefficient of permeability is constant. So I think in the permeability chapter, this coefficient of permeability will be discussed. So what he assumed that this coefficient of permeability is constant throughout the experiment. Then Darcy's law is valid. So what is Darcy's law? This will be also explained in the permeability chapter. So this Darcy's law is valid for this case. Okay. Then consolidation is one-dimensional problem. So what he assumed, consolidation is a one-dimensional problem and water flows in only one direction and the resulting settlement. That means settlements only happening in one direction, in vertical direction. Because of that, it is called one-dimensional consolidation theory. That means deformation only happens in one direction. Okay, and water flows in only one direction. And the last one is soil particles are assumed to be incompressible. Soil particles are not compressible. Whatever the settlement happened, this is due to the expansion of water. So these are the assumptions made in the Tarzaki's one-dimensional theory. Okay, this is what happened. This is sand, clay. These are nothing but porous stone. This is porous stone. This is the clay. This is undisturbed sample. This is the height of the sample. Okay, so this is the entire thing. Now what I'll do, I'll share a video with you. So all of you, please go through the video. Okay, go through the video and try to understand what happens in consolidation. Okay. So this is how this odometer is, the soil samples are prepared. You look at how soil samples are prepared. See? So we use vernier calipers to measure the diameter and height of the this consolidation ring. This is called consolidation ring, where the soil sample is kept. And you have to find out the weight of the consolidation ring. So this is an undisturbed sample. You can prepare disturbed sample also. See how this sample is prepared. Now the excess soil sample is removed. What he did, he trimmed the excess soil from the ring. Okay. Now he is taking the weight of the ring with along with the soil sample. So why he took this one to find out the moisture content. So this is called filter paper. This filter paper is placed in between soil sample and the porous stone so that the soil particles do not enter in the porous stone. Okay. Yeah. This is the collar. This is screw. These are used to tighten this entire soil sample. This is the porous stone. Top porous stone. This is movable. This is top porous stone. It should move freely. This is the porous disc. Okay. Now what he did, he placed the entire thing in the loading frame. This is the loading frame. This is how loading will be given. So is fully saturated. Now what will happen? He will apply some water in the soil sample to make the soil saturated. This is a dial gauge through which this dial gauge is used to find out the deformation. How much deformation is taking place? This is calculated using this deformation. This is dial gauge. This is a dial gauge. Okay. This will be This will be adjusted to the soil sample, and this will give us a reading of the deformation. When there will be deformation, no, there will be changes in the dial gauge. Okay. Now he is using a level to ensure that the loading arm is completely horizontal. This level is used to make it horizontal. Okay, and there are some screws also through which we can make it. Yeah, this is a loading frame. So here we apply the load. Okay, release the jack screw and take the dial gauge readings at required intervals. Okay, so load plates are added. Okay, so once the experiment is done, what we do, we remove the soil sample, we see we again take the dimension, okay, how much deformation has taken place. Initially it was 2 centimeter, and after consideration how much it reduced. Okay, yeah, okay, share this lecture PPT. Okay, yeah, I'll share. Okay, yeah, I'll share the lecture PPT. But the thing is that have you understand? Have you got a slide? No. Have you understand how this consolidation is done? What is consolidation? Huh? Students? Did you understand what happens? Okay, yes, ma'am. So now, this is what happened. No soil sample. Then there is a porous stone. In between this porous stone, we place some filter paper so the soil do not enter in the this porous stone. Okay. Then there is a loading. No, this is the cap. Then under there should be a ball. This ball is used for the uh, proper even distribution of this load. Then this is the pressure. Okay, this is the color. This is the water. This green color is the water. This is given to keep the soil sample fully saturated. Okay, throughout the soil sample throughout the test. Okay, then it is written soil specimen placed inside the metal ring. Diameter is actually generally 6 centimeter. Even though it's written 50 to 70 to 75 mm, generally what we use 60 mm, 6 centimeter diameter this ring. Then height is 2 centimeter. Generally we use 2 centimeter. So you can do from undisturbed soil sample or you can use disturbed soil sample also. Then specimen kept submerged in water throughout the test. Load is applied to a lever arm. This is lever arm. I think you have seen the lever arm. Okay. Yes, I think it's in the next slide. Yeah. Okay. These are the this is a loading frame. This is a lever arm from which load is given. Right? Okay. So what data we get from construction? There are a lot of data we get. Initially, the change in body shape with time under different load. See, like for a particular load, no, there will be a specific the there will be specific deformation, right? If we apply 100 kPa load, so there will be deformation. If we apply 200 load, there will be more deformation. Okay, and for each and every load, no, there will be a 90% consolidation. Okay, so from like generally what load we applied in the laboratory 5 kPa, 10 kPa, 20 kPa, 50 kPa, 100, 200, 400, and 800. These 8 different load we applied. This is a cumulative load we applied to the soil sample. Yeah. So any question? Okay, this is the load increment data. Can you see this? This is a S curve. Okay, sigmoidal curve. So this data we get from the consolidation test. Okay, this is a deformation and this is time. Okay, time this can be in second or you can take it in minute, and this deformation in mm generally. Now from the dial gauge reading we get the reading of deformation. Okay, this dial gauge minimum this one reading is I think 0.002 mm. Okay, so what happened when we apply the load to there will be deformation with time. So initially this is the deformation, then this will happen, and after that there will be it will come at this stage. So this node from where this changes node. Okay, this point is called initial compression. From here to here, this is called primary consolidation. This initial compression is nothing but the deformation that is takes place just immediately after the application of the load. That is called initial compression. Okay, after that, from here to here, this point is called primary consolidation, and after this is primary secondary compression. It takes actually a long time. Actually, this secondary compression to consolidation, this takes lot of time. Actually, sometimes years also. Okay, so this is the three different consolidation, these three different stages we get from a consolidation curve. Okay, and from this curve only we can find out the what is pre-consolidation pressure. This I'll explain in the next class. Okay. So I hope everyone has given your attendance. 30 students are present. I think all of you have given your attendance. Okay? Student? Hello? Am I audible? If you have given no, don't give again. Okay. 001. Yeah. So you can leave the meeting right now. I'll take the next class and the next week. Okay, zero. So you can leave the meeting, huh? 007 00 21.